This is the video lecture for Chapter 4, Correlation and Prediction. The objectives for this chapter include being able to calculate statistics to determine relationships between variables, calculate and interpret the Pearson product moment correlation coefficient and the standard error of estimates, use scatter plots to interpret the relationship between variables. First, we will talk about the correlation coefficient, also referred to as R. The correlation coefficient is an index of the linear relationship between two variables measured by the Pearson product moment, or the PPM, correlation coefficient, symbolized by lowercase r. R scores range from -1 to +1. This association can be depicted by a straight line. It indicates that the magnitude and direction of a relationship. When we have a positive R, it generally means if the participant scores above the mean on X, they will usually be above the mean for Y, or the second variable. A negative R means those scoring above the mean on X will generally be below the mean on Y. An R of 0 indicates no relationship. A +1 or a -1 are equal in strength, they're just opposite in direction. If we look at this figure, which is figure 4.1 in your book, it shows us those attributes of R. As we can see, to the left, we have our negative numbers, and to the right, we have our positive numbers. We can see a -1 is a perfect negative relationship, and a +1 is a perfect positive relationship. As we get farther away from 0 and closer to positive or -1, the strength of the relationship increases. This is an example of some sample data. As we can see, if we were to look at the values for the chin-ups and the pull-ups of the different participants, we can see that there is some sort of relationship. Those with high chin-up scores tend to also have high pull-up scores, and those with low chin-up scores tend to have low pull-up scores. If we calculate the R, we would get a direct relationship or a positive relationship. On the contrary, if we look at our body weight in relationship to pull-ups, we see that those with a lower body weight tend to have a higher pull-up score, and those with a higher body weight tend to have a lower pull-up score. If we were to calculate R here, we would get an inverse relationship or a negative relationship. So as body weight goes up, pull-ups go down, whereas as chin-ups go up, pull-ups also go up. We can plot this in a scatter plot, which we can see on the next slide. Here's an example of a scatter plot for that pull-up and chin-up data from the previous slide. If we look here, we have pull-ups on our x-axis, chin-ups on our y-axis, and each different dot represents a specific individual. If we were to add a line to this graph around most of the data points, we would kind of find this direction, which is a positive direction of the data, or a positive correlation. This is a scatter plot of the correlation between body weight and pull-ups. As we can see here, weight in pounds is on our x-axis and number of pull-ups is on our y-axis. Again, each dot represents a specific individual. If we look at the overall trend of this graph and a line were inserted, it would be in this direction, or a negative direction for a negative correlation. We've talked about positive and negative correlations, but if two variables, their correlation coefficient or their R value is 0, or their 0 correlation, then the scatter plot does not resemble a straight line at all. And so this is an example of a 0 correlation. All of the dots are just kind of randomly placed. There is no trend to them. So how do you calculate R? There are some statistical softwares that can do this for you. However, it's really important that we understand where these numbers come from, so we are going to go through it by hand so that you have a better understanding of how we calculate R. The first thing that you have to do is arrange the data in paired columns, so X and Y. We then square each X value and each Y value and place the results in two additional columns, X squared and Y squared. I will go through this step by step as we go through. And then we want to multiply each X by its corresponding Y and place the results in a new column called the cross product, or the XY. Our next step is to determine the sum for each column. So the sum of X, the sum of Y, the sum of X squared, the sum of Y squared, and then the sum of XY. And then we're going to use the below formula to calculate R. Remember that the N, the lowercase n, is the number of different participants or the like that you have in your data. So here we're going to actually calculate our correlation coefficient, or our R value, for our chin-ups in relation to our pull-ups. So we have our participants in the left-hand column, then we have our X. If we had referenced back to our previous table, those were all of the individual chin-up scores, and then it's summed at the bottom for a sum of 76. Each of those individual X scores were each squared to get our X squared column, and then our sum is 686. We also have our Y column, which is from the data of our pull-ups, the number of pull-ups they completed. It's summed for all participants of 65. Our Y squared, which is then summed to 501. And then if we take our X values, multiply it by our Y values, we get our XY column. So 10 times 8 for participant 1 is 80, participant 2, 9 times 7 is 63, and so on. So now we're going to use the equation below to kind of build our equation to get our R squared, or our R value, sorry. So if we look, we have our R, and then our N, number of participants, is 10, so we're going to start with that. Then we're going to multiply that by the sum of our XY. So if we look, our XY value is 576. We're going to take that, and then we're going to subtract our sum of X times our sum of Y. So if we look, our sum of X is 76, and then our sum of Y is 65. And then that's going to make up the numerator part of our equation. So then we're going to divide all of that by the square root of 10, which is our N, again, multiplied by our sum of X squareds, or our 686. Subtract that from our sum of X, and then we're going to square that sum. So 76 squared. And then we're going to multiply all of that by 10, again, our participants, times our sum of Y squared, which is our 501, minus our sum of all the Y's squared, or our 65. Sorry, that should be the 65 squared. The wrong box is highlighted. And then if we calculate all of that, we'll get an R value of 0.89. Remember, the closer our value is to +1 or -1, the stronger the correlation. So an R value of 0.89 is pretty strong. So how do we interpret R? The first thing we want to do is check the direction. Is it positive or negative? And if it's a positive sign, one variable increases and the other variable also increases. If it's a negative sign, one variable increases and the other variable decreases. A negative correlation can occur if two measures have opposite scoring scales as well. For example, if we wanted to know how quickly someone could run a mile, the one with better endurance would have a faster or a lower time. If we had those same people do the pacer test, then the one with the better endurance will complete more levels and have a higher score. So we would have a negative correlation because they would have a higher score on the pacer, but a lower time on the mile. Another reason for a negative correlation is if two measures that measure different things have a true negative relationship. So, for example, those who are heavier or have a higher body weight tend to complete fewer pull-ups. So that's more our true negative relationship. So after looking at the direction for R, or the positive or the negative, we want to look at the degree of the correlation. Remember, our degree is going to be from 0 to 1 on the positive or the negative side. So from 0 to -1 or 0 to +1. Again, the closer it is to positive or -1, the higher the relationship. So this is a scale that's often used. So an R value between 0.80 and 1.0 is a high relationship. Between 0.60 and 0.79 is a moderately high. Between 0.4 and 0.59, moderate. Between 0.2 and 0.39, low. And from 0 to 0.19 is no relationship. Again, these are positive or negative values. Our third step when we're interpreting R is our coefficient of determination. So it's the square of the correlation coefficient. So R squared. So in our previous example, we had an R value of 0.89. If we squared that, we would get 0.79. So that R squared value represents the proportion of shared variance between two measures. What that means is the percent of variation in the Y that is accounted for by X. So how much is one variation accounted for by the other variable? It's also how well is the regression line at approximating the Y value. So how well is that line that we get that on that scatter plot, how well is that at approximating the value of Y for each data point? Our fourth and final component of interpreting R is our significance test. What this is a test to determine whether the value of a correlation coefficient is statistically significant. For example, if the correlation is not 0, how statistically significant is that? And it's based on something called our p-value, and we're looking for a p less than 0.05. If a p-value is less than 0.05, the correlation is considered statistically significant from the value of 0. So it's saying that there is a correlation of some capacity. Sometimes p-values can be modified. Sometimes you'll see a p-value of 0.01, which is more rigorous, but 0.05 is pretty common. If the p-value is more than 0.05, there is no statistically significant correlation between the variables. An example of this would be BMI and percent body fat. Thus, the correlation is interpreted as being 0. So if it's not statistically significant, then the correlation is interpreted as being 0. While R is commonly used, there are some limitations to it. For example, if the relationship between the variables is what we consider curvilinear, then the ppm correlation coefficient will underestimate the true relationship between X and Y. The ppm will only indicate a linear relationship. So if the ppm of a curvilinear relationship would be near 0, It's helpful to graph this as a scatter plot so we can see if there is a curvilinear relationship. And I'll show you an example of what that looks like on the next slide. Here's an example of a curvilinear relationship. As we can see on the left side of the graph, as our x's increase, our y's increase. But after about 5, we can, on the x-axis, we can see that as our x's continue to increase, our y's decrease. If we have a relationship like this, the Pearson product moment, or our PPM, is going to underestimate the true relationship between x and y. Remember, we can only calculate r if we have a linear relationship, so not something that looks like this. There are some additional limitations of r. The first is that correlation does not necessarily indicate cause and effect relationships. Sometimes a third variable may be the cause of the relationship detected by a high R value. For example, we would expect to see a high correlation between elementary grade and shoe size. However, both of these are related to a third variable, which is age. So the younger you are in general, the smaller your shoe size. And then thirdly, R is greatly influenced by the variance or range of the variables measured. Variables with a large variance or ranges tend to have higher R values than those variables with a restricted variance or a restricted range. So it's something to make note of. Here's a visual example of range restriction. The value of R in either the solid or open dots are much smaller than the value of R for the combined data. This is because the variance is greater in the complete set of data than in the subsets. So the biggest thing is that the interpretation of the value of R goes beyond just noting its magnitude. We also must consider other issues such as how linear it is, other related variables, and the variability of the data involved.